Hey, I'm recording my lecture today, but I'm going to make it available to you. So Jonathan will send you a link, so you can also refer to it for your study. So the main topic for today, I would like to talk about the multi-panel design pattern. I believe Jonathan started you with this pattern here already, right? I believe maybe from last week, he talked about the problem itself and also the first design attempt about how you can have spaghetti code using GoTo. And also, he talked briefly about the functional approach, basically, right? Like without the OO. I'm going to briefly review what the problem is, and then I'm going to talk about the first and second design attempt, and let's focus more on the third design pattern, which is OO, which is why we want to study this particular pattern. Okay, that's going to be the roadmap. And if we can finish earlier, then we can talk about composite a little bit, and then he can pick it up from there on Wednesday. So the for every design pattern, we have to know what kind of problem we are trying to solve. And for the state design pattern or multi-panel pattern, you want to solve problem for interactive system. Basically, the system doesn't really terminate, but it's going to interact with user with some feedback. For example, if you have some online booking system, just show you very quickly. So this is kind of the problem we are trying to deal with. Let's say if you have a flight booking system. So you can, let's say on the initial page, you can enter departure city, you can enter destination city, and etc. So once you confirm about your return dates and departure date, you can hit enter, and then they'll bring you to another page. You can think of essentially you are transiting to another state of your system. Okay? That's a very typical usage for such interactive system. And then, okay, I'm sure he showed you the picture about that. So that's like a simplified view for the system that we're dealing with. So how can we model such system? So you don't really want to jump into code right away. That may not be the recommended way of designing your system. You want to think about what can be the abstract model. And I know you guys are in the engineering program. You don't really study like a theory to computation, but just about state machine. Okay, I'll just show you quickly what I meant. Basically, what we're going to assume is we're going to have a finite state system, finite state machine. For our system, have different states and different transitions. And this is the running example for this lecture here. Okay, let me just go over with you very quickly. Okay, if you have this particular state transition system over here, so you can think about this is the abstract view. So you got different states over here, and typically with the arrow, we say that's the starting states of your system. Okay, that's just initial. And then for each state, you can have different transitions depending on what you want to do as a user. Okay. On the right-hand side is actually so-called state transition table. And you're simply just trying to specify precisely, for example, let's say if currently I'm in the initial states, and then the user say, I want to do action number 2. The corresponding entry is going to show me I want to go to state 5 as a result, right? For example, so what this will correspond to is I'm now in the initial states over here, and then I'm trying to take action number 2, transition number 2, basically. And then I'm going to go to state number 5, which is confirmation. Okay, so the table there actually summarizes such information. Okay? And question for you guys. I would say the diagram there is pretty abstract view of the system. Try to model it using a finite state transition diagram. What about What about a transition table? How can you implement them? Let's say you want to implement this in your favorite programming language, not just in IFO, right? Could be in Java, could be in Python, could be any other language. How would you turn this table into implementation? Can a single array do it? Not really, right? It seems like more than one dimension. In that case, maybe a 2-dimensional array, right? Okay, just to remind you about what you should know. Okay, maybe from the first year, I'm pretty sure when you learn the Java course in 2010-21, you learn about array, but now we're adding 1 dimension to it. Okay, so the state transition table here is something that we're going to put into the implementation eventually. Okay, that's going to be the main control. Okay, and then for the very first design, let me just go very quickly since you already talked about it last week. The first design simply say you're going to define your overall system as a label system, basically, right? Since we got, let's see here, how many states do we have? We have 1, 2, 3, 4, 5, and 6. we got 6 different states. In that case, you got 6 different sections. You got section 1, section 2, section 3, all the way to section 6. Okay? Every section there is going to be defined in a similar fashion, okay? In a similar way. Well, since we are trying to deal with an interactive system, so what each section should do is to say, for example, if I'm currently in state number 3, okay? So now state number 3 over here corresponds to state number 3 here. I'm now in the state where I'm trying to inquire about what seats are available to me, okay? And then for every state over here, I'm actually going to say, I'm just using a from until loop to show you that it's actually ongoing interaction with the user. Okay. What we're going to do is, to begin with, we're going to display some information about this current states to say, okay, so now you're in the seat inquiry state. So these are, you should really enter maybe your departure dates, enter your return dates, and etc. Okay. And the until part is really important, right? Since we're trying to use the until loop from iPhone. So this until says, until this is actually true, we're going to exit. When it is not true, in that case, we're going to stay in the loop. Okay? So we're going to say until it's not the wrong answer or the wrong choice. Basically, what this will do, you got to work out the logic yourself to think about, we're going to run the loop as long as the user cannot provide with us the valid answer. We're going to keep prompting them until they actually got a valid one to us. Okay? And then we're going to do a little bit more over here. You're going to read some answer from the user. You're going to read their choice for the next step. And also, you want to say if the answer they enter was actually wrong, in that case, you're going to give them some feedback, right? And then finally, if everything the user has entered is actually correct, in that case, you're going to process their answer. And then you're going to say, depending on their choices, it can be 2 or 3. So over here, you can see in state number 3, either you go for action 2 or you go for action 3, right? These are the 2 choices. And this is just the pseudocode. How about that? This is more like the pseudocode for state number 3, okay? To really see the drawback for this particular first design, you have to consider if I want to define other states accordingly, what would they look like? Right? That's the question you're going to think about in order to judge if the design is good. Typically, your design should not have lots of duplication, right? Remember, there's a principle we have learned so far. Do you guys know about single choice principle? Single choice principle. Okay. Let me just take this one for example. For others, you can also refer to your notes or my slides. Okay, just talk about this one. That's a very big drawback for the first design. First of all, what's single choice principle? Okay, anyone try to paraphrase it? What's single choice principle? What's single choice? What does it really mean? Guys, any idea? Well, let me help you a little bit. Every time you talk about a design principle, you really want to think about if you're trying to make certain changes to your design. And that design is going to have some consequence. And the design principle is going to judge whether the consequence is going to be either good or bad, basically, right? So every time you want to judge the design principle, you have to think about changes. Okay? You want to give it a try? What's single choice principle? If you remember, that's okay. If you don't remember.
I think it's only using like one variable in your decision making. The user will only deal with one decision that they make at a time. You won't be making decisions multiple variables because with one variable that you're basically controlling, you can basically make your choice off that and just branch through that instead of anything more complex. So it's with the state machine that makes it.
Okay, it's not. Okay, maybe you're talking about something else. You're trying to say, try to keep your system simple, right? Not to branch out too much. But single choice principle is talking about something else. But that's okay, okay? Anybody else? Anyone else? You want to be, actually it's good to be wrong, during the class because this might be something we ask you in the exam. In the exam, we may not even tell you a single choice principle. We simply give you the first design and say, criticize it, right? In this case, one of the answers we would expect to hear from your answer will be single choice principle, number 1. Number 2, why does it violate single choice principle? Okay, let me just mention very briefly. Okay, we don't want to stay in this first design for too long. Okay, now basically single choice principle tells you, okay, when you make a change, when making a change, there should be minimum number of places to make such change. And typically, when we say minimum, we mean just one. You should be able to make your design in such a way that every time you want to make a change on your design decision, there should be only one place. Okay? So now let me help you a little bit to explain why the first design actually violates the single choice principle. Over here, we only show you the definition for state number 3, right? You can imagine that for all the other 5 states, okay? For example, if you also try for state number 4, for example, right? For 4, it's going to be reservation. And you can imagine that because the way we interact with the user will be very general, it's actually defined in a very general way over here. So that means you have to repeat more or less this particular loop in number 4 over here. You're repeating basically, okay? And also the way you process the user's answer might be a little bit different, but again, you got to do some case analysis over here. That part will also be very similar, okay? So that's duplicating from number 3 to number 4. And similarly, you have to make such a duplication for all the other 5 states. So now, imagine that if today, just make a very simple change. Let's say I want to get rid of this particular condition over here from my interactive pattern. If I want to delete this particular condition here, how many places do I need to modify to get rid of this condition? Is it just one single place? Not really, right? Because this particular pattern has been duplicated to number 4, number 3, number 2, number 1, number 5, etc. So I need to go to every one of them and get rid of this particular condition manually. So multiple places. So it's a violation of single choice principle. Okay? So maybe when you're doing your lab or the projects, always think about if you want to make a change to your design, how many places do you have to go? If you have to go to so many places, it's violating single choice principle. Okay, duplicates basically. Okay, I don't want to spend too much time on the first one because we already talked about. Okay, what I want to go to is the second design. Okay, I'm going to make the slides available to you, very similar to Jonathan's. You can also refer to them. Okay, that's the first design. Let's talk about the second design. I would say you will only go to the first design when all you have is like assembly language at your hand. So you don't typically want to go for the first design because, well, if you got Python, if you got C#, if you got IFO or Java, you definitely got OO solution, or at least a procedural solution. So this is not the way to go. Unless you only got MISP available to you, then you might choose this design. Okay. The second design is going to be something where you don't have really object orientation supported, like a C, for example, right? All you got is functions, or maybe modules, or maybe records. Okay, it's more like more criticism about the first design. I'll let you study that later. The second design is really about top-down hierarchical solution. Okay, I will point out exactly how that works. Maybe Jonathan covered that already last time, but just review the essence of that. Okay, for this particular one, we're going to have some separation of concern. So we're going to have at least the huge improvement right now is have a transition table. Okay. And the transition table is going to correspond pretty much to this particular table over here, basically. Okay, the implementation detail I can leave it up to you. You can study that offline. Okay, I'll just point out to you. And also, you can, as I said, you can use a 2-dimensional array to implement your state transition table. And for your information, in IFO, it's called array 2. You can look up this particular class. It's a 2-dimensional array. Okay, for your interest. And then there's a transition function there, and the obvious pre and post condition we have to write is to make sure the source states and also target state, they should be within the range, right? Since we got only 6 states, so they should be within 1 and 6. Okay, quite obvious. Okay, the pre and post condition. And then, okay, so that's more like a transition table. That's how we implement it using a 2-dimensional array. We'll revisit this particular array a little bit later. Both the second design, which is not OO, and also the third design, which is OO, they both use 2-dimensional array for that part. Okay, that part is really the same. Okay, but for now, since we don't have OO, let's see what we have to compromise in our design. Okay, I will just go there directly. So that's the overall structure for the hierarchical design. Okay, let me explain that a little bit and show you a little bit more code. And then we have to go to the major criticism about this design, which does not have OO. The idea would be, you can think about this particular function over here. Okay, we'll just talk about function. Let's use the terminology you have in C programming language, right? In C, you don't really have command versus query or mutator versus accessor, just function. You can think about the execute session is the entry point of execution, entry point of execution. If a user wants to use your system, they're going to call execute session first, only call that function. And then that function there is going to have different sub-functions. So you can think about it at different level. The entry point is like a level 3. Somehow just follow the textbook convention. But you can think about it as level 1. Doesn't matter. Okay? The first level is execute session there, which has 1, 2, 3, and 4 sub-functions. And each one of them is going to do something specialized for that particular purpose. And for this particular sub-function over here, we got sub-functions, basically, right? The execute states is really the main sub-function you have to pay more attention to, which I'm going to show you in just a moment, okay? You can think about this is basically a sub-function whose behavior depends on the current states. Depends on the current states. So here, when I say the current state, it's a very interesting question, right? We haven't really gone through exactly how we're going to represent the current states. But since we are talking about a state transition, finite state machine. So, for example, if I'm trying to take transition number 2, taking transition number 2 from a context state being 1 versus taking transition number 2 from a context state being number 4 will have very different behavior, right? It really depends on the context, okay? So now, the concept about current state is really important when you want to solve this kind of problem. You can see for both states, by simply taking transition number 2, you can see you have different outcome, right? It can either be number 3 in this case, or it could be number 1 in this case. Okay, that's my point here. Okay, let me go back there and then show you a little bit more code. Okay, let's see the top level here, right? Basically, this guy here is the top level I just talked about over here. Let's see a little bit more detail, okay? You can see this guy here is an execute session, right? In which case, we're going to call the 4 sub-functions. Let's see the pattern over there. You will see the pattern very similar to how we did it in the first design attempt. So now you can see we are trying to represent the current state using just integer, which makes sense because we got 6 different states. We got 1, 2, 3, 4, 5, 6, right? And using integer, you got 2 to the 32 possibilities that you can encode into the states. That should be more than enough. So the current state and also the choice, which is a transition you might take, would be integer. And then you still use a from until loop. You're saying from, to start with, the current state should be the initial states. You can think about the initial here simply going to return some number, which will be the initial state, which can be 1, can be 2, can be any other states. And then you have a sub-function here called isFinal. You basically keep running your system, keep interacting with the user until you reach the final states of your system. In that case, maybe the user has paid, they have confirmed their itinerary, and then they exit, they log out, right? That'll be the final state, for example. And then in the body of the loop, every time, you have to see execute state here, right? Remember I mentioned that. So this is the most important sub-function here that we're going to talk about, okay? Depending on where you are currently, you're going to execute the state differently, okay? We're going to see that in more details. Okay, and then after we have done the current state, we'll do whatever we should do, and then you're going to transit the states, maybe from 2 to 3, 3 to 4, and etc. Okay? Guys, I'm going to pause a little bit here, and then do you have any questions at the top level? So now we're talking about design number 2, and then what I just finished was the top level, level number 3, according to your slides. But I can think about it as an entry level. What we're going to talk about next will be specifically how you can do the execute states, okay? And notice that the execute state function here takes current state as an integer. Notice that, okay? That will actually indicate something that could be potentially a flaw in the design, okay? We're going to criticize on that. Get prepared for that. Okay, so that's the top level here. And then what we will do is we're going to say execute states. How do we execute the states? So now you can see as part of the as the parameter, I mean the input for this function here is current state, which is integer. Okay. So now we're going to say we get let's have a local variable here, some answer, valid answer, etc. Okay. So these might be changed if you want to program specifically for your system. So they are just over there as a sketch. What we will do now is to say for every state, we're going to say until the user actually gives us a valid answer. Maybe they're trying to give us their credit card number. We're going to validate it, right? If they give us some invalid number, we're going to keep prompting them for the valid credit card number, something like that. And then for every state, this is how we're going to do it. First of all, you're going to display some information about the current states. If the current state is about sit inquiry, then you have to display maybe a calendar, for the itinerary. And then you're going to say whatever, depending on what its current state is, we're going to read some answer from the user. Maybe in this state, you will take a departure and return dates from the user. In another state, you will take the credit card number from the user. Depends. And then you're also going to take a choice from the user. Because maybe in the confirmations page, the user might choose to log out, let's say. In the payment page, the user might choose to say, I want to choose another payment method, right? Really, again, it depends. Everything depends on the current state, really. That's why they are all taking as parameter the current states. And then you're also going to validate, it's called the correct, right? You're also going to validate the current states, the answer. Okay, we're going to say if not valid answer, then you're going to give them some error message. Okay. So what we have said was about this particular subfunction, which I said is very crucial. Think about the execute states itself. Is going to display, read, correct, which means validates, display error message if necessary, and also to process in order to go to the next stage. Notice that every one of them, the execute state is going to take CS for current states, integer. Display is going to take the current states. Read is going to take it. Every sub function is going to take it. So you can think about each sub function here takes as input current states. Okay? So now we have seen all the three levels. So now we should have enough ground to criticize about the design. Okay, we'll get there. And then, so now, so this is just like a summary of what each routine is supposed to do. Okay, exactly how you do it is not important for the discussion here. Just at least you know that we got different sub-functions, and every one of them should know what the current state is, and then behave accordingly. That's the main message here. And here is my question for you. Okay, if you imagine that you're going to implement display, re-answer, re-choice, correct, process, and message. If you're going to implement every one of them, how similar will they be between sub-function to sub-function? How similar will they be? Or they will look very different. And in order to help you about judging this design, number 2, you may also want to think about single choice principle, which we just reviewed, right? Okay. Basically, single choice principle tells you you really should not have duplicates whenever possible. But now, in this case, do we have duplicates?
Yes, like for display, you have different cases for different states.
Okay, let me write down exactly what you are saying so everybody can share. It seems to be on the right track. Why don't we try? Basically, you're trying to sketch for us the solution for, let's say, display, for example, right? Okay. Let's say this. The display function over here has current states, integer. Okay? Let me just say for now. Okay? Go ahead. Just sketch it out. What should I say? Let's say we use if and else, let's say. Okay, you say if the current state is equal to 1. Okay? Okay, very good. Then we maybe display something specific to state number 1. And then else if, okay, that's good. Current state equals 2. And then we display maybe something different. I'll use a different color over here. And then etc. All the way to, You might say else if the current state equals 6. So since currently we got 6 different states. And then in this case we'll have maybe blue. Different color simply means you may have to behave differently depending on the current state. Very good. Thank you. Maybe other functions as well. Let's just choose another one, okay? And let's say, how about message, for example, right? And to really make the points, I can simply just copy and paste whatever I have just read or what I have just written. And then if I copy and paste, which means I got lots of duplicate, right? The only thing I have to change is something like this. I have to say, for example, let's say, first of all, I'm talking about message. As soon as I'm done with that, would you agree I should keep this control structure to say if current state is 1, else if current state is number 2, else if all the way to current state is equal to 6. And then all I have to do is to make sure I redefine this part over here to say how I should message back to the user when it's state number 1, and how I should message back to the user when it's state number 2, and etc. So what's being duplicated? Yeah, so let's say here, so this is one subfunction. This is just another subfunction. So from function to function, what's being duplicated? Is it the branching condition, or is the body of the branching condition? Branching condition, agree? Okay. What you should notice is, let me just highlight it. This part here is exactly being duplicated, whereas this part over here is okay. This part here is fine because depending on different states, you just have to do it differently. But now somehow but you are still duplicating the structure. Okay. Nice. Have you followed so far? Good. Of course, since we got how many subfunctions? I forgot. Let's see. Since we got 1, 2, 3, 4, 5 different subfunctions, right? 1, 2, 3, 4, 5. I have to duplicate this particular control structure 5 times. Agree? Okay. Good. Now let's follow up from that. Having said that, since we got so many duplicates, but why is this a bad design? How would you justify it? Let's say this is the exam. What we will show you is like this. This is the question. We say, one way to implement a multi-panel system is by having the second design, like a hierarchical approach. And these are examples where how you can implement the level 1 subfunctions, right? And every one of them takes as a parameter CS, current states. Given this, how can you justify it's a poor design? Exactly. Very good. Thank you. That's exactly right. Actually, not just to add the new states. If you want to make some state obsolete, you also got to delete certain branch, right? Okay, let's illustrate this. It's very, very good. That's exactly what you should say if you were asked. Let me make the case a little bit simplified here. Let's say I'm simply going to sketch. You got state number 1, you got state number 2, maybe I'll just make it up. 3, 4, 5, 6. Okay, let's say that's our finite states machine. Okay, let's say this is what we got. We got from 1 up to 6. Okay, it will violate single choice principle. I totally agree. But now here's how you illustrate. There are 2 scenarios at least. If you're trying to add a new states, let's say I'm trying to add state number 7, which is going to look like this. Let's say the red one, right? It's a new change. In that case, do I have to modify just a single place or multiple places? Multiple, right? Right? Because I got to say, for example, I'm going to say else if over here, current states equals 6, and then I'm going to display it differently. And also similarly, going to say else if current state equals 6, and then I'm going to do something here, right? Okay, that's one illustration already, right? You have to modify multiple places. If you, huh? Oh, 7. Thank you. I definitely meant to write 7. Good. Okay, so now in this case, of course, depending on how many subfunctions you got in level number 1, If you got 100 subfunctions, you got to modify 100 times manually, right? Notice that manually, okay? It would be very nice if somehow the runtime system can keep track of such stuff for us. It would be very nice, okay? But let's just watch it out a little bit more carefully. Okay, another illustration very quickly. Let's say if we design another change, let me use maybe purple. Another one is, what about we want to delete a states? Let's say delete a states from our system. Let's say the state number 2 should no longer be there. In that case, not only that I have to get rid of this in one place, but also every subfunction I have to get rid of this, right? Again, it violates single choice principle. Okay, hopefully that's clear to you. Guys, any questions? We okay? Okay. So the second design, the most important criterion you should really understand is about single choice principle. Because somehow, for the design number 2, we don't really have the notion about objects versus classes. Because for every object, you can declare its type. But now, in such language like a C, procedure-wise, you don't really have a way to really automatically know what's the type for the objects. So that's why we had to manually encode it using the current states. Okay, that's some insight into the problem. Okay, we're going to see exactly some comparison in just a moment. Okay, just bear with me. Okay, that's something we already covered. Okay, so I'm just going to go over. Okay, again, you can see the current state is basically just carry over for every function. And we know that it's pretty bad. Okay, and what I want to do is now to talk about how we can move from design number 2 to design number 3. That's really what we want to see. Okay, you can think about we are basically moving from C into some OO language, either Java or iPhone or C#, right? Things like that. How can we do it? Let me show you the fundamental difference over here. So this is the most important slide to understand. Okay, think about this guy here being design number 2, right? Hierarchical design. Okay, and then, oh, I beg your pardon. I decorated the wrong picture. Let me do it again. So this is the hierarchical design over here, right? You can see it's got sub-function everywhere. Okay, so this is top-down. This is our design number 2. And notice that for current states, we simply say integer over here. And then for every function, we have to give current state explicitly as the input, the parameter. Okay, that's a second design. In design number 3, which is the actual multi-panel state pattern, in that case, what we do is as follows. Current states is now no longer a single type like integer in the second design. Instead, it is of type some class called states. I will explain the architecture for the state pattern in just a moment, but we'll see. So now you can see the current state is of type states, and more to it. Notice what we're trying to do over here. Current states dot execute session, right? If you try to compare how we called the two features in the 2 design. In the previous design, when you say execute session, you must give the input, explicit input. But now, when you say current states dot execute session, you can see the current states is actually implicit. That's the critical difference. Okay, any questions? I want to show you the syntactic difference first of all. And then we now have to, in order to move more smoothly to design number 3, can anybody tell me if you can imagine how polymorphism and dynamic binding is going to work for design number 3? Okay, design number 2, we have no choice because we don't have OO, possibly, right? But for design number 3, we do have OO. And one characteristic feature about OO is inheritance. I'm pretty sure you guys will review about inheritance, right? Earlier. So this is design number 3. And now I'm going to show you exactly, but I want to see if you guys can imagine before I introduce that to you. How do you think polymorphism and also dynamic binding, how these two OO constructs are going to help us to achieve these? Okay? Guys, any thoughts? I will just hold it. Yeah. Anything you want to say? It's okay to be wrong, or if you are worried about saying something that doesn't make sense, that's okay, right? How about this? Let me start with this. Can anybody tell me what's polymorphism? You can even give me an example, that's fine. What's polymorphism? Okay, start with you.
Like an example would be, I would declare a state, and then I could like cycle through an array of states, and
Okay. You're saying you got states, an array of states? Not too bad.
so like if I declare a variable that's a state, so that's the parent,
Mm-hmm.
and then the children, I can assign that variable to any of the children.
Mm-hmm.
Object that inherits from a state, so it gives you like state one.
Mm-hmm.
If the state one has a certain variable is A, then it would be an example of polymorphism because I define the parent state, but I can still identify
Mm-hmm.
children.
Okay.
Dynamic boundary from the past that declare the parent, and then if I say dot display that
Mm-hmm.
it's going to dynamically bind to whichever children's state.
Okay, dynamic binding is pretty good. I would say for the polymorphism, what you're missing is about the notion about static type. That's what's missing there. Okay, good. Okay, good. So polymorphism, okay, let me just mention abstractly quickly, just by using something simple example, and then you're going to see exactly that when I present to you the architecture for the multi-panel pattern, okay? Let's say this. Let's make it very general. If I have, let's say, A here, I have B here, and I have C here. Okay, it's a very simple hierarchy of 3 classes, where A is a superclass or parent class, and B and C are the child classes, or in a more general way, descendant classes, right? Because hierarchy can be multi-level. In that case, you wouldn't say children anymore. You're more like a grandchildren, right? So that's why we say descendants. Okay. Anyway, that's just an aside. Okay, so now polymorphism means if I declare objects of type A, okay, and then polymorphism, poly simply means multi, morphism means shapes. It simply means objects can have different attachments at the runtime, okay? So how can we do that, right? So now one way to do it, for example, I can say creates, and then remember the syntax for IFO is you put a dynamic type over here, right? What the actual object should be. So now I can say B here, and then I can say obj.make, assuming that make is defined in the class, okay? And then I can say creates over here. Also, I can say C here, obj.make. Line number 1 and line number 2. Both lines actually compile in IFO. Or for those of you who may not be very comfortable with the syntax here, okay, let me show you quickly. Number 1 here is equivalent to if I say if I say A, obj is assigned to new, and then B. Okay, some constructor over here, right? The A here corresponds to the A here, B corresponds to the B here. Okay, but you shouldn't really think in Java. Well, it's just a different syntax in this language here. Okay, so both 1 and 2 actually compiles, because what's in the curly brackets over there is a descendant class or a child class of the static type A. Right? B over here is a child class of A. C over here is a child class of A. So they are fine. Okay, there's some rule you have to know about doing assignments. Okay, more to it. You can think about what we're doing is, for 1 over here, we're saying obj, by executing 1, is now going to point to dynamically some objects of type B. Okay, that's what 1 would do for you. Okay, and then when you try to execute number 2, in that case, you basically say object is not going to point to wherever it is currently pointing to anymore. Instead, it's now going to point to another new object. Dynamically, it's going to be C. Okay? So now you can see for the same variable over here, it might have different shapes, either B or C. But there's a rule over here. Whatever dynamic type you're trying to assign object to, they must be descendant classes of its static type, which is A. So A is so-called static type. Okay, hopefully that will be a nice review for you about static type versus dynamic type, right? So when you talk about OO, so these are very important concepts. Okay, dynamic binding goes one step further. When you talk about dynamic binding, you're really talking about what's going to be the runtime behavior for your objects. Okay, let me just recreate 1 and 2. 1 and 2 just illustrate you how, like you can have multiple shapes for your objects. For 1 and 2, I can insert a little bit more code to show you dynamic binding. Okay, let's make the following assumption, right? You guys know about how to draw bond diagram, right? Hopefully, we're going to give you some feedback on lab number 3 soon. Okay, let's say in class A we have feature F, right? And then we say plus to say if feature F is implemented. Okay, it's not abstract, it's not deferred. And let's say in each of the child classes, you can choose to either inherit the F verbatim, or you can redefine that to something else. So here, let's say F, what should be the notation to say is redefined? Plus plus, good. Just quick check. Okay, good, plus plus over here. So what I will do now is to do the following, okay? For number 1, okay, I'm gonna rewrite it, so it's a self-contained example. 1 here, when I say creates B objects dot make. Number 2, I would say obj dot f. And then I'm going to say number 3 here, creates C obj dot make. And number 4, obj dot f. What I want you to pay attention to is 2 and 4. But the numbers here indicates the order of execution. So we do 1, and then 2, and then 3, and then 4, right? For 2 and 4, you can see the context objects, obj, are the same. The feature that we are trying to call is also the same. Would you think we're going to get the same runtime behavior from 2 and 4 or not? I would say it depends on how you redefine F in B and C, right? Oh, sorry, in B and C, yes. Okay, so very quickly, so that's about dynamic binding. When you actually reach the point about executing number 2, at this point here, just after executing 1, you know that obj is now dynamically pointing to B, as we drew previously. So now dynamic binding simply means which version of the feature that's going to be called depends on the actual dynamic type. Because now the dynamic type is actually B, so now we'll call the version of F from B. Okay, so now the F over here comes from B, so I'll put B here. Okay, you're gonna see lots of occasions like this for dynamic binding when we talk about different design patterns. And then later on, the next one. After executing line number 3, we basically reattach. We're reattaching obj to obj rather than pointing to over here. It's now going to point to an object of type C. Right? Now if we apply the same principle, when you say obj.f, which version of f is going to call depends on what the dynamic type is. In this case, C. Right? So that means it's going to be from class C. Okay? It's a very quick summary of polymorphism and dynamic binding. Okay? You will see the same application of these two concepts or interplay with them, actually over and over. Okay? Any question about polymorphism and dynamic binding in general? Everybody's okay? Okay? Okay. So now, what I would like to do now is to, based on polymorphism and dynamic binding, we want to see exactly how we can move from the top-down non-OO solution into the OO solution, where the states itself represent the root of some inheritance hierarchy. That's what we're going to see. Okay? So now we move to Design number 3. Okay. Design number 3 is going to be so-called state pattern or multi-panel pattern. Right? Doesn't matter. Now, before I show you some implementation, before that, what I'd like to show you is the architecture. Drawing the bond diagram. I'll make the architecture diagram to you as well today after lecture, so you can also refer to it. Okay. Let me illustrate exactly how we can do it. So one technique you want to pick up from this course is you don't really have to see the code before you know how the system works. Just by seeing the architecture diagram, you should have some reasonable idea about how things work. Okay, let's see. Okay, let's go over the diagram quickly. First of all, this is the application class, right? You can think about this as a client. And then we have a client-supplier relationship. And then you can imagine that in the client side, we declare some feature of type states. So this is a very important hint about how you can use a state pattern. So you can imagine that, I'll write it down quickly. You can imagine that if this is your implementation, when you have class, application, and then somewhere you got feature, let's say somewhere in the middle, you say, let me just, okay, states is of type states. So this one here indicates some client-supplier relationship. Okay, that's why you got this particular label here. Okay, that's first of all, that's how you use it. And now, how does the state hierarchy look like? That's important, okay? So now we'll see. The top level, we have the class called states. And notice that it is deferred. Deferred simply means you cannot create an instance directly out of the states. You have to go to its concrete or effective descendants to create their instances. So what are the possibilities? So basically, wouldn't be too surprising, we got 6 different descendants. Somehow I got 7, but you can, however many you have should correspond to your state diagram. Okay, you can see 1 descendants for initial, 1 for help, 1 for final, and etc. 5 inquiry, 6 inquiry, reservation, and confirmation. And notice one thing here. You can see this arrow over here is a different one. So this guy here is client supplier, right? And this arrow here is for inheritance. And you should really be very precise about which arrow you should use. For example, when you try to design for your lab number 4 in the projects, what later design efforts, it should always be clear about what kind of architecture I should have among the classes. Either should it be client supplier, or should it be inheritance? Or maybe they simply don't have any relationship, right? That's more like a design decision you have to make. So now this is inheritance, and the fact that we have, you can see this is basically a cluster. This cluster, I just call it state implementations. You can see the inheritance relation here goes from the cluster over here to the states. So that simply means it's as if I said initial inherits from the states, flight inquiry inherits from the states, help inherit from the states, and etc. Right? I just like a shortcut for me. Just make the diagram less complicated. Okay? So you can feel free to use that technique for your lab design documents. Okay. So far, any questions? What we have introduced was just this particular client supplier and also the class hierarchy, right? Let's now talk about what features we should declare. Okay? Let me enlarge this to really make my points. Okay? All the features will be declared at the parent level, which means everything will be inherited to the descendants, okay? Either deferred or effective. Okay? Now I want to, first of all, point out the feature that's going to be, depending on exactly what the current state is, they will be deferred at the state level. Okay? You can see the state over here. Okay? We got read, we got display, we got correct, process, and also message. Okay? Let me make a point over here. So all these features over here, the reason that they are deferred is because, okay, deferred because implementation depends on the states. If I make the read defer over here, that means when I go to the initial level, I have to redefine, I need to implement read in one way. If I go to the flight inquiry, I have to implement read in another way. So I don't really know exactly how I should implement each one of them, read, display, correct, etc. in the state level. I simply don't know. Okay, that's why. Okay, and did you notice that there was one feature there that's actually not deferred? Hopefully you noticed that, right? Let me point it out. Okay, that one there is called execute. And notice that it's plus, which means it's effective. Before I said that, the reason that all these features are simply deferred because at the state level, I don't necessarily know how to implement it. It's more state dependence. On the other hand, for the execute over here, it is actually effective, which means I know how it should be defined. Okay? So inside the particular state pattern, there is another small design pattern we have to learn. Okay, I'll put it here. Okay? It's called a template design pattern. Briefly speaking, I'm going to show you exactly how it will work in just a moment. Template design pattern. What this means is exactly how this execute will work. I'll show you the code. Maybe that'll be easier. But the template simply means whatever implementation we have over here is going to be inherited to initial, to flight inquiry, to other classes, right? We don't need to change them. Okay? I'll get there. And having this, that's about it for the architecture. Okay, you just have to know there's one single feature in the state level that's effective, which is execute. Okay, that's called a template design pattern. And so now it shouldn't be too surprising to you. If I declare S to be of type states, dynamically you can polymorphism. You can either be sit inquiry, or it could be confirmation, right? You can see both classes are descending class of states. So that's polymorphism, right? And then more to it is about dynamic binding. If I say s.execute over here versus s.execute over here, it's now going to make sure it will call different versions of the execute. But you might be wondering, it seems like there's only one version of the execute over here, right? In some way that's true. However, as we'll see, the execute feature here, even though it is implemented, but it's the way we implement it is by referring to defer feature. Okay, we're going to see exactly how that's going to happen. Right? That's an interesting bit about this example. Okay, well for now I'll simply mention this. Okay, I'll just write it down, and then we're going to see exactly how it's going to happen. Okay, there is only one definition of execute, which is in the state class, right? The execute. However, when I say only one definition, that's why it's called a template, right? That's why the name, template pattern. However, behavior of s.execute depends on its dynamic type. Dynamic type. Okay. Let's see exactly how this is going to be the case, right? In case you cannot really catch up with the taking note, that's okay. I'm going to make things available to you, so you don't have to worry. Okay. So now let's take a look at the code very quickly. Okay. And let me just show you a little bit of animation over here, just for the code. Okay, so this again, from moving from state, design number 2 to design number 3, we want to get rid of all the explicit current state arguments. Okay, that's the architecture, and let's see how we can define the state class. Let's see. Let's say we have a class called state that's deferred, okay, which means you can never create an instance directly out of the states. And then we have the read. Notice that it's deferred. We have answer. Okay, just something like a local variable, like attributes. Also, we got choice, we got display, we got correct, we got process, we got message. So far, you have seen all the defer feature in the state class, right? Remember, there was one class as set that was a defer, that was effective, which is this. let's take a look at the execute feature, which is interesting. The interesting thing is the execute feature itself is implemented. However, its implementation depends on things that have not been implemented yet. That's the interesting bit. Okay, let me show you. You can see for execute here, I simply have some local variable called good. Okay, and then I will simply say display. Display is referring to the display over here, which is deferred, right? And also I got read, I got also correct, I got message and process. Okay. Now I have seen all the code here. Let's see. Notice that here, the execute feature over here, this is effective, is implemented. Okay, that one we know because it had the do and body, right? But now you can see that the display, the read, the correct, message, and process. Okay, all these features, if for example you can see display, it's over here is deferred. The read over here is also deferred. The correct over here is also deferred. The message over here is also deferred. The process over here is also deferred. Within a particular effective feature, we refer to defer features mainly. But it's still valid. It will compile. Okay? Guys, any questions so far? Okay? In order to understand this more properly, we have to simulate what's going to happen at the runtime. Okay? Everything up to here, basically everything compiles. Nothing wrong with referring to defer features within effective feature. Nothing wrong with that. Okay? That's actually the beauty about dynamic binding. So now, let's think about what's going to happen here. Okay? Let me give you a little bit of hierarchy. Let me simplify. Rather than reconsidering with all the 6 classes, let me consider only 2 classes. Okay? Let's say this. I have my state class over here at the top, right? That one's deferred. Let's say I talk about sit inquiry and also confirmation, right? These 2 classes, right? Under which I have sit inquiry and also I have confirmation. Okay, it's 2 subclasses. And execute is effective. Okay, and then display, for example, I'll just talk about 2. Let's say display and read. So display and read, display is over here, and read is over here. They are both deferred, right? Display is deferred. Read is deferred. And notice that all the descending classes of state should be effective, which means every deferred feature they inherit from the state must be implemented, right? Okay, good. Now, the way to draw that on the design diagram looks like this. So I would say like this. Display plus read also plus, and also display plus, and also read plus. But notice that the display over here versus the display over here may not be the same because they are in different states, but they have to be implemented. Okay? Any question about the diagram? It's about architecture. I just show you a simplified version. Okay? So now you got deferred feature in the state class, but at the descendant level that's effective, you must implement all the deferred features. Okay? That's the setup. And now we have enough ground to trace the code a little bit to see how exactly the template pattern works. Okay? Now let's take a look at this fragment of code. Let's say, first of all, we declare S to be of type states. Okay? S is now going to point to some descendant class objects, at the runtime. Okay? For states. Apparently, this is a valid attachment because C inquiry over here is a descending class of states, so that's a valid. Okay? So now, as soon as I do that, S is now going to point to a objects of type sit inquiry. Okay? Now, my question for you. Now I try to execute this particular line, s.execute. Okay? now we can be a little bit more detailed about how exactly things are going to happen. Okay. Number one, what's going to be the version of execute to be called? Let's answer question one first. Which version of the execute feature is going to be called in this case? How many versions do we have, by the way, for execute? One, right? Because I only got execute plus in the state class. You can see in the states, inquiry, and also confirmation, I didn't try to redefine that. So there's only one version, right? So that's the only version that's going to be called. Okay? Version in the state class. Basically, this version here, execute. Okay? The next question is more important. Okay? Version of, since we're going to call this particular version over here for the execute, unavoidably, we have to somehow execute display. We also have to execute read, for example, right? They'll be part of the execution. What will be the version of display and read to be called in this case? Don't tell me it's going to be the version from the states because they are just simply deferred, right? Okay? Anyone? Yes. Why would that be? Why would that be the seat inquiry version? Why? I agree. Oh, yeah, I agree with you. You're saying because the display and read are deferred in the state class, so that's why seat inquiry and confirmation, they all implemented. They both implement this read and display feature. But how do you know which version should be called? Should it be the version in the seat inquiry, or should it be the version in confirmation? How do you know which version? Exactly. It'll be based on the dynamic type. Okay, good. So now dynamic binding tells us, even though you are executing the same pattern over here, but because at this point here, S is dynamically pointing to seat inquiry. So that's why it's going to call display and read from this version here. Okay? It's going to be from seat inquiry. Guys, it's very important understanding here. You can see, even though we are executing the same version of execute from the state class, but now because at the state level, they refer to display and read, they are actually deferred. So that means that we are leaving to the descending classes to implement them. But now dynamic binding is going to make sure the correct version is called from descending classes. That's the essence for template pattern. Okay? Continuing with the same logic here. Okay? If I try to do, let's say this, let me use blue. Okay? If I try to execute, let's say this particular line here, right? So now that means S, rather than pointing to here, is now going to point to this particular object of type confirmation, right? And then when I try to say S.execute again, right? Similar question. For question number one, what will be the version of execute to be called? In the states, because I still got that one and only version. Okay, so it will still be the states version. Okay, I'll put in blue so you can see the both versions. And now, what about the version of the display and read? Dynamic binding tells me which version to call for display and read depends on what the dynamic type is. And now, because of this particular line, I have already changed the dynamic type for S from seat inquiry into confirmation. So now, dynamic binding will tell me I should really call the version from confirmation. So I would say they should be from confirmation. Okay. So I would say in order for you to really understand the state pattern and also the template pattern working together, you have to understand exactly how these lines are being executed, especially think about which version of the feature is being executed. Okay. Any questions about this? Everybody's okay? All right. Yeah. Okay. Have you guys found this more interesting or iterative pattern? Maybe? Equally good? Equally bad? Anyway. Okay, so now let's talk about how you can, so we pretty much finished about the state design pattern. So now we just have to give you a little bit more context about how you can implement it. So we just go over some code. And then one final point we should make in a moment is about how you can create a polymorphic collection of states so you can do state transition. We'll get there, okay? But I think if you understand up to now, you're pretty much set up you're pretty much set for understanding the whole pattern. Okay, the template design pattern is exactly what I just said. Okay, so when you read the slide, you can see you can read the written form for confirmation. Okay, so now let me show you the diagram first. Right, so this is really eventually how the system is going to work at the runtime. Okay, let me point to you very quickly, and then we'll see how to make it happen. Okay, you can think about something like this. Eventually, what we will get is like this. We have some application, the clients, and then the client, you got an application which is the main supplier for the state design pattern, right? You actually want to have our application could be maybe booking system, let's say. And then you should have some transition table. The transition table is just basically an array of two, like a two-dimensional array. And then this guy here, it simply tells you, if I am currently in state number 1, I'm trying to take action number 2, I should go to state number 5, for example, right? Just encode very simple state transition behavior. And then over here, the states array is the interesting bit. Because we know that every time, if I say current states dot display, for example, because now in the OO approach, I don't need to explicitly pass the input parameter over here. So what I need really is, at the runtime, I just need different instances for different states. I got initial here, I got flight inquiry, I got C inquiry, and etc. Okay? Notice that states is array of states. So what that means is, if I say this, let me just show you exactly how things are going to happen, and then we'll see the coding very soon. Okay? The coding itself will not be too bad. Let's say we declare such array over here. If I got current states, it's simply states. And let's say for the states array, let's say index number 1 dynamically is pointing to initial. Index 2 dynamically is pointing to flight inquiry, and etc. Okay? So now if I say CS, current states, is assigned to states at position 2, for example. And then after that, I say CS dot display. Okay, let me just give you one more line. Okay, it's a very important line to understand before you see the whole everything. Another one, I can say current state. I'm going to change that to maybe states at position maybe 5. And then after that, I can say CS dot display. You can see now, I have two lines over here, CS.display and also CS.display, right? The same context objects and the same feature that's being called, okay? Are the two lines I just highlighted, are they going to give me the same behavior at the runtime for display? Not really, right? Hopefully you can see why, especially from the diagram. Assuming that we set up an array, it's called polymorphic array. Okay, let me just mention that quickly. You will see that in the slide as well. So this is so-called polymorphic collection of states. So when you declare the static type, you simply say states, which is deferred. Dynamically, it can be any of the descendant classes of states. Okay, and then after this particular line, you're saying that CS is actually pointing to index number 2. So dynamically, it's now going to be flight inquiry. So now when you say CS.display, it's going to call the version from flight inquiry. Similarly, so now when you say CS is assigned to state number 5, rather than pointing to here, number 5 is pointing to basic confirmation. You're saying CS is now going to point to confirmation over here. Dynamic type has been changed to confirmation. So now when you say CS.display, it's now going to call the version from confirmation. Okay? It's a very important operation you should understand. when the state pattern work. Okay, you have some top level transition diagram over there as a two-dimensional array, and also in order for you to change the current state from one dynamic type to another, you simply got a collection, polymorphic collection of the states from 1 to 6, could be grown later. And then as you change the current state from one dynamic type to another, for example, when you say CS.display is going to give you a different result. Okay? So when you study the multi-panel pattern, that's the points you want to focus on. Okay? I got about maybe 10 or 15 minutes. Let me just go over, finally, the code quickly with you so I can finish the multi-panel pattern. And when Jonathan comes back on Wednesday, he will pick it up from composite. Okay? So what I would do now is to show you a little bit of code. You can interrupt me if you got any questions there about the coding. Okay? Let's do that quickly. Okay, that's the diagram I already explained. The actual application class, okay, as I said, is going to be of transition array 2. Okay? Two-dimensional array. And then also you got an array of states, and notice that the state here is a deferred type. Dynamically, it can be any of the descending classes that are effective. Also, okay, we got initial, we got number of states, also we got number of choices. So these are important attributes for you to write some nice invariants to really make sure the state is within, for example, 1 to 6. Action should be within 1 to 3, something like that. Okay, so some invariant over here. So the application class itself is not that complicated, right? You just got different attributes, especially these two, transition and also states. So these are the two main things to pay attention to. Okay. And then just continue from that. I just repeat the same fragment, okay, but it's the same class. And you got different commands to actually add a new states. Okay, I'll leave that to you because this one I can see pretty much like for one-dimensional array. If you want to add something to the array, you'll say force. Similarly for a two-dimensional array. Okay, so you can also say choose an initial and etc. So these are simple commands you can write. Okay, just to say now I want to add a new transition into my diagram. Okay, and then let's see some example over here. Okay, what I want to do, I'll show you the code one by one first of all, and then we'll see how we can trace it. Okay, basically you create some new application. You're going to say, I want to have 6 different states. I want to have 3 potential actions for each state. Okay, just have it parameterized. And then I'm going to create different states. I can say the put the states and create initial.make. What this will do is it's going to make sure at index 1, you're now going to create initial state as the first one. You do the same for index 2. That should also point to flight inquiry. Index 3 point to seat inquiry, etc. Okay, you do 6 such lines. And then you also choose the initial state. Let's say state number 1 is the initial states. And then you put a transition. This one, I'll just give you one example. This one is to say, over here, given, let's say, for example, if you're currently in state number 2, and then you're trying to take action number 3, and then you should go to state number 3. Okay, that's kind of what the put transition will do. Just modify the two-dimensional array accordingly. Okay, that's really implementation specific. I'll leave that to you. And then over here, you say the index, which is about the index for accessing the state array. It will just be initially just the initial states. Okay? And the current states, you can see over here, the current state here is assigned to certain elements in the states array, right? You can see exactly like how we did here. Current states, current states. You might assign that to either index 2 or index 5, depending on which index value it is, right? So it depends. Okay, and then after that, you can simply make sure it's an initial state, right? And then you might do some transition there, and now the index will be the resulting states after making the transition. After that, you can update the current states. Could be that. Can we just see one example quickly? Okay, how about this, very quickly. Let's say this. Let's say what I want to show is over here. Initial states, let's say index is simply initial. So that means the current state should be initial states. You can think about current states. Current states is basically the initial state dynamically. So you can think about this is the current state conceptually. This is the current states. And then what we want to do is to say, let's say the user's choice is actually number 3. If you see from the diagram, by taking this particular transition with choice number 3, what we should end up having is state number 2. Agree? So now what we do is we're going to call this particular line to say index should be updated to, we want to have a lookup table into the transition, right? So now currently index is simply just 1. And then I'm taking, this is the current states. And then the 3 is the action. So now if I go to this particular table over here, if I'm currently in index 1, the current states, and then I take action number 3, I should have the resulting states, number 2. Okay, this 2 is my return value from the transition table. So index 2 is now 2 over here. And then what I will do is I will say current states will now be changed to the second elements in the states array. In that case, I'll say CS, rather than pointing to the first one, is now going to point to the second one, which is flight inquiry. Okay, it's a very quick run through of the code. Okay, I would say when you study that, try to look at the sample code more carefully. Okay, and then something similar. This one just try to show you overall how you can actually do the state pattern, right? Just overall interactive system. Okay, similar. And this slide here simply summarizes all the ingredients for making things work. Okay, coding-wise. Okay, finally, this is a summary slide just to, again, emphasize you should know about what's really the fundamental difference between the non-OO approach versus the OO approach. In the non-OO approach, you have to give the current state as explicit input. Right? In the OO approach, you simply declare some inheritance hierarchy, and then depending on the dynamic type, when you say s.display, you no longer have to say the state number explicitly anymore, like a 1 and 2 over here. You don't have to, because dynamic binding is going to take care of everything for you. So the lesson from this lecture here, if the language you're trying to do your design supports OO, of course you should really choose the design pattern. If they don't, unfortunately you have to go with the non-OO approach. But you know what the drawback is, especially violating the single choice principle. Okay? Guys, any questions? We okay? Okay, I think I was, around time. Okay, I'll finish maybe a few minutes earlier. And then when Jonathan comes back on Wednesday, he will pick it up for the composite pattern. All right?